Thank you. So I'll talk about joint work with Moshe that is sitting here and Noam that's sitting here. I'll talk about competition between sellers that sell items that complement each other. Sorry. Okay, it will take some time. Okay, so one major field in economics is called industrial organization, and in this field, they study competition between firms and how properties and the structure of the market affect the outcome of the competition. And it turns out that industrial organization is important, and it has several implications. For example, a regulator like the antitrust authority that needs to approve or disapprove mergers and acquisition between firms needs to know what is the meaning of a merger before approving it. Also, an individual firm need to know what is the outcome of its decision to acquire some other company, etc. And even mechanism designer needs to know need to understand the structure of the competition. For example, when we design two-sided platforms, market platforms over the internet, where sellers compete with each other, we need to know how to accommodate or facilitate the best trade, most efficient market. And it turns out that algorithmic thinking and algorithmic tools are pretty useful in understanding these questions, these aspects. We'll see that we use approximation, dynamics, computation in the analysis of this such competition. Okay. So there are many ways in which companies compete. They can run advertising campaigns. They can decide how many units to produce. We will focus on maybe one of the most fundamental forms of competition, on price competition. In this competition, the only strategy that is decided by the firms is what is the price of their product. But before analyzing the market, the competition, we need to understand what are the relation between the items. For example, the items can be substitutes. If I own an iPhone, then probably my willingness to pay for Samsung Galaxy is lower. However, if I bought an airline tickets to some holiday destination, then actually I need to also book a hotel room in order that my flight reservation will be valuable for me. Okay? So we see that sometimes some items are substituted to each other, some other items are complements, and in this talk we will try to crystallize the effect of items being complement on the competition in the market. So we will focus on the case of complement items. Good. So let's see an example. Consider two firms. This is supposed to be the red firm and the blue firm. Each one of the firms owns a patent. Okay, this firm owns one patent. The blue firm owns another patent, and they can give licenses to other companies to use these patents. So now, first firm A, charges a price of PA for using its patent, and the other firm B charges the price of PB. And now consider a case where another company, a third company, wants to use the two patents together in order to produce its own product. Now, the other company needs to purchase the rights, needs to pay this payment in order to get the license to use the first patent, and needs to pay PB in order to use the other patent. So overall, needs to pay the sum of the two prices. So what happens here is that although the two firms sell completely different items, these are two different items, A and B, they indirectly compete because there is some buyer, the third firm, that is willing to buy the bundle of the two items together. So in this case, if the third firm buys only one of the patents, this is completely worthless to this firm. It needs to buy the bundle of the two items together. So the two firms actually compete for the pocket, for the money of the buyer that is willing to buy the two items together. Okay, like in the example of the airline and the hotel, actually these are completely different products, but because there are buyers that are willing to pay to buy the package of the two items, they have some competition on the willingness to pay of the buyers. Okay, so let's talk about the demand. Of course, there may be multiple buyers. Each one has some different willingness to pay for the bundle of the two items, and we can draw a demand curve that show the demand for the bundle of the two items. So here, the demand curve can show for each price of the bundle, which is the price of A plus the price of B, how many units, how many buyers would like to pay to buy this bundle of the two items. Okay, so this is a standard demand curve, but this is the demand curve for the bundle of the two items. There is zero demand for the two items separately. Okay, so now let me summarize the model. This is the model that we study in the paper. There are two monopolistic sellers of two items, A and B. There are no supply limits. They can manufacture as many products as they want, and it's free. So manufacturing is free, no manufacturing costs. And as I said, A and B are complements. This is called perfect complements because if a buyer buys one item separately, the value for the buyer is zero, and the value for the buyer for the whole bundle, A and B together, is VI. Okay. And also, this is a full information. This is a full information game. The buyers are not very interesting. We assume that the values are known. Their decision is very easy. They see the price and they buy the item if they want to. It's not an incomplete information game. The two strategic players are the sellers. And they know exactly what are the values. They know exactly what is the demand curve. So it's a full information game, no hidden values here. And finally, we'll consider a demand curve which is not continuous like this, but it's more like a step function. We assume that there is a finite number of possible values for the buyers of VIs. And this actually measures the complexity of the demand, and we will use this the number Okay, so the answer is not very intuitive. So the answer is that monopoly is better for society in this case. So why is monopoly better for society? So it is clear that monopoly is better for the firms. They earn more money if they hold all the market power. But here, the surprising thing is that the consumers are also better off from having a monopoly. So the monopoly price will be lower than the price where we have two competing firms. So this is observation done by Cournot a long time ago. And in this work, we try to quantify Cournot's observation. And in the same model, we would like to compare the revenue of the monopoly and the revenue of and the equilibrium revenue. We'd like to compare the revenue in different types, in different equilibria. And also, we want to see how the market converges to equilibrium. We will study dynamics that converge or not converge to an equilibrium and see if it goes quickly and what is the result. Just a comment, I'm talking only about revenue here, but everything I say is also holds for the social welfare, for the efficiency. We have parallel results for everything for social welfare, but I would in this presentation I will only talk about revenue.
Question.
Yes.
I think I missed something. So the buyer's valuation is known.
Yes.
So how is the monopoly not just fully extracting?
So it's one price. It's one price. You cannot. It's not fully full discrimination. Good. If you heard one of us talking about a similar model, we had another paper on a similar model. In this model, the demand structure was in this paper. The demand structure was simpler, but in the other paper, we studied a model where we have a network of sellers. For example, if I have some item that complements Moshe's item, and Moshe's item complements Noam's item, then we can draw a network of these complementarities. And in the other work, we studied how the structure of the network affects the behavior of the equilibrium behavior in the market, but I will not have time to talk about it here. Of course, there's a vast literature on the algorithmic price competition and vast literature in I/O, in game theory, and related topics, but I will not talk about it here. Okay, so in the remaining time, I will try to survey the results that we have. If I have time at the end, I will give you some taste of the positive result that we have. Good. So the concept that we use is Nash Equilibrium. Of course, we have two sellers, and if the price of one is the best response to the price of the other, and vice versa, this is a Nash Equilibrium. And if you think about it a bit, it is very easy to note that Nash Equilibrium always exists. For example, if the two-seller price at infinity, it is clear that this is a Nash Equilibrium, because if the other one prices at infinity, what can I do? Nobody will buy anyway, so I can do whatever I want. But this is a non-interesting Nash Equilibrium because nobody buys. We have zero revenue and efficiency. So we need to study, to focus on non-trivial equilibria, and this is what we do. We define an equilibrium to be non-trivial if we sell something. A Nash equilibrium where we sell some item is non-trivial, so from now on we will focus on non-trivial Nash equilibria.
Are there infinite?
Pardon?
Are there infinite number of Nash equilibria? In the continuous way, continuous curve.
I guess so, but I don't know. Yes.
Full complementary. The items are fully.
Yeah, perfect complements.
So there is no equilibrium where there will be no equilibrium where someone buys one item.
I know.
Pair of pairs.
Every buyer one pair.
An item is a bundle, a bundle of items.
Okay.
Yeah, but I will show simple examples very soon. Okay, so we have actually three types of result. We have existence result. Then we show how bad are these equilibria, and then we study how the dynamics that lead or do not lead to an equilibrium. So the first question is, I defined some refinement of Nash equilibrium, non-trivial equilibria. Do they exist? It sounds trivial to prove that they exist or not, but we needed to work. It's not that easy, but the answer is affirmative. There always exist Nash equilibria, non-trivial Nash equilibria, and we even give an equilibrium that computes an efficient algorithm that computes such equilibria in the game. So if I have time at the end, I will show you how to do this. But then after we know that non-trivial equilibria exist, we will note that not only that they exist, sometimes there are multiple equilibria. Okay? And then we need to figure out the property of the worst equilibria or the best equilibria. So let me show you an example. So here we have two sellers priced at PA and PB. We have one blue buyer that is willing to pay 2 for the item, and we have 100 buyers that are willing to pay 1. So overall, we have 101 buyers. And let's start by noting what is the monopoly price. If I want to if I control the two sellers and I want to make the most money, what should I do? Well, it's clear that I will target the value of these 100 yellow buyers, and I will price it 1. If I price it 1, then all the 101 buyers will buy from me. Okay, this one will also buy at 1. So my revenue is 101. And it's not reasonable to price below, because then I will just I'll have the same number of buyers, but they will pay less. And if I price above 1, then all these 100 yellow buyers will not buy anything. So the monopoly price is to price at 1. For example, if each one of the sellers prices at 1/2. And now the question is whether this is an equilibrium behavior, and the answer is yes. It is an equilibrium. Why is it an equilibrium? Because let's have a look at the red seller. The red seller gets 1/2 from 101 buyers. So it's approximately 50 revenue of 50. The only thing it can do, because they take all the surplus from the yellow buyers, but they can also target the surplus, the remaining surplus from the blue buyer. But if he increases the price, then he will get only revenue from this blue buyer, which is like 1.5 instead of getting 50. So there is no beneficial deviation for each one of the sellers. So this is an equilibrium. Okay, an equilibrium with good revenue. Now, the problem is that there is another equilibrium in this game. For example, if both players price at 1. This is also an equilibrium, because given that the other seller prices at 1, actually all the red player cannot get anything from the yellow buyers. So it's a best response to price at 1, and then he gets 1 from the blue buyer. Okay? So this is another equilibrium. So we see that in one equilibrium, the total revenue is about 100. And in another equilibrium, the total revenue is 2. So there is a large difference between equilibria in this setting. Yes, Nick.
Like 0.3 and 0.7 is also?
It will also be an equilibrium, but 0 and 1, no, 0 and 2. No, it's also an equilibrium. Yes.
Almost everything.
Yeah. There is a range of equilibria here. Okay. So now let me use some notation. I will use D as the total consumer value in the system. This is the sum of all values. I will normalize the smallest values, the lowest value to 1. We don't need it, but just for this presentation. So actually, using this simple example that I showed you, we see that there are settings where the worst equilibrium gets us a revenue of 2, like a small constant revenue, and the maximal profit, the monopoly profit, is in order of D. Okay, and this is the conclusion from this simple example. The bottom line is that sometimes some equilibrium may be really bad, up to a factor linear in D. Okay, what about the best equilibria? Maybe although the
when you say D, you assume the minimum price is 1, or what? Because you can
yes.
multiply B.
Yes. For this presentation, I assume that the minimal value is 1. But in the paper, we have a general. We don't need this assumption. So maybe there are always good equilibria. Okay? Maybe we can always find a good equilibria. So how bad are the best equilibria in this system? So and the answer is that they are not too bad. They're not as bad as we saw before. And the theorem, this theorem is that the monopoly revenue can be larger than the best equilibrium, but only by factor of square root of D. It cannot be as large as we saw before. It's only by factor of square root of D, which is good news for us. And actually, we can improve it.
Can you remind what's the
Monopoly price, if you control the two sellers and you set the price that will get you the highest revenue, that's the monopoly price. If they merge into one monopoly and act together. So actually here, something is wrong with the animation, I guess, here. Well, okay, never mind. So the third type of result that we have here is about the way that the firms, the market reaches the equilibrium. How do they reach the equilibria? So there are a lot of ways to analyze this repeated game or dynamics. You can use no regret dynamics or analyze the subgame perfect equilibrium or use a discount factor, etc. What we do is we take the most basic dynamics that is known, maybe the most popular, which is the repeated best response dynamic. The best response dynamic is a simple dynamic where one of the players optimizes the price given the other price, and then it is the turn of the other player to optimize its price, and so on and so forth. And this is a myopic behavior. Okay, this is the main criticism. This is a myopic behavior because each seller optimizes the price based on the current situation without seeing the implication the future. And the bottom line of our result for studying the dynamics is that the dynamics lead to poor equilibria. And not only that they lead to poor equilibria, they do it very slowly sometimes. Okay. Let me elaborate on this. Okay. So a main issue when studying best response dynamics is the starting point. Of course, if we start at an equilibrium, we will stay there. And if we start at the best equilibrium, we will stay at the best equilibrium. So, but it's not reasonable that they will know how to start the dynamics in the best equilibrium. Usually we need to think about some natural or reasonable starting points. So what is a natural or reasonable starting point? First, we can think about zero prices. That is, start with very low prices and then start the updating process. Or the second solution is maybe they have some agreement. They start with some cooperation. They agree to be a cartel, to be together, to form together a monopoly, and they split the monopoly profit between them. And then it is known from the literature that the cartel solution is not stable. So one of them deviates, and then they start some chain of reaction. The third reasonable way to analyze the starting point is choose one at random. Okay? So what we show is that if you start the the best response dynamics at each one of these starting points, you will fail. Okay? Let me show you one example. What happens if you start with zero prices? So let's go back to the previous example that we had here. This is exactly the example that we had before. We have 100 yellow players that are willing to pay 1, and 1 blue player that is willing to pay 2. And now let's run the best response dynamics. So what should the red seller do? He should price at the monopoly price. He's like a monopoly now, so he should price at 1 and get revenue of 101. And now it is the turn of the blue seller, and the blue seller knows that he can get nothing from the yellow players, but he can get 1 from the blue player. So this seller will also price at 1 and get a revenue of 1 from this player. So this will be devastating for the red seller, but the blue seller is selfish. He doesn't care about the red seller. He cares only about his own utility. Okay, so this is what we saw here. We saw that the best response dynamics leads us to the worst equilibrium, to the very bad equilibrium that we saw before. So one conclusion is that starting from zero prices is not a good idea. We can see it by this simple example. For the other cases, we need to work more. We have theorems. For example, in some settings, best response dynamics starting from any split of the cartel solution of the monopoly profit will lead us to market failure, to the worst equilibrium, which is quite bad. I don't want to get into details. And we have another theorem that tells us that if we start with random prices, prices that are chosen uniformly at random between 0 and the maximal value, then in some settings with probability 1, we will get into a very bad outcome, which is approximately linear in D or proportional to 2 to the n. And finally, the last result that I want to tell you about is about the time to convergence, how long it takes for us to converge to an equilibrium. Well, the third theorem is that it can take arbitrarily long time. Okay, even for 2 demand levels, if we have only players with 2 different values, then we know that the best response dynamics can take arbitrarily long time. For any number you want, it can get more than this number. But the good news is that it always converges. Okay, for two demand levels, it always converges. It always terminates. And here we have one main open question is that we don't know if in general the best response dynamics always converge.
Theorem 3 is worst case. What about worst case? What about random or uniform starting points? Do you have some analysis? Theorem C is for worst case.
Right, it's for worst case.
What you have
For random, I don't know. I don't know if we have result for that.
So it's not easy to come with an example when it takes infinite time, that like the epsilon is always halving or something like that. And it takes infinite time to reach equilibrium.
Right. For if the epsilon becomes smaller, your running time will be larger. It's not infinite. It always terminates for 2 demand levels.
No, but if you have arbitrary function, I mean, it's not easy to come with an example
For
that
continuous demand.
Yeah, continuous.
For continuous demand, yes.
Yeah.
Yeah.
Okay.
When you say demand level, these are the prices, the population, do they have 3 possible prices? Demand price?
Pardon? Can you repeat?
Can you remind what the demand level is?
Yeah. It's the number of steps in the demand function.
Okay.
It's the number of distinct values. So I will conclude with the main open question is that we don't know if the dynamics always converge. Even for 3 demand levels, we don't know this. We only know for 2. Okay, and I'm out of time. So just to summarize, we show that algorithmic thinking can be helpful in analyzing competition environments like this. And some future work is, which is quite important, how to model complements and substitutes together in a tractable way. We still don't know how to do it. That's it. Thank you.